We know that FPGAs are mainly characterized by the presence of three building blocks: configurable logic blocks, input-output blocks, and interconnections. We got already familiar with CLBs and IOBs, but we need to know more about interconnections. The interconnection resources within an FPGA allow the arbitrary connection of CLBs and IOBs. The main modes of interconnection are direct and segmented. Direct interconnection is made of groups of connection that cross the device in all its dimensions. Logic blocks put data on the most suitable channel according to data destination. This implementation usually includes some additional short-range connections that link nearby blocks. Segmented interconnection is based on lines that can be interconnected using programmable switch boxes. Also, in this kind of interconnection, there are lines that cross the entire device in order to maximize the speed of communication and limit the signal skew. On one hand, segmented interconnections offer a reduced power dissipation because of resistance and capacity of the interconnection lines are only those of the interconnection length between the blocks. On the other hand, the main advantage of direct interconnection is that parasites resistance and capacitance are almost constant, resulting in an improved predictability of the propagation times of the signals. Therefore, having the right mix of both is going to guarantee us the best performance. Let us now consider an example to better clarify how the interconnections are working. The three building blocks presented so far, CLBs, IOBs, and interconnections, interconnect together in the device to create a communication infrastructure composed of the communication lines and IOBs around b-dimensional array of CLBs, which covers most of the available die area and represents the true FPGA building block. In this figure, we can see simplified FPGA composed by 2 times 2 CLB structures, 8 I/O blocks, and 5 switch boxes. Considering that we are focusing on the interconnections, let us now focus just on the 5 switch boxes. More in details, we are interested in knowing the internal structure of a generic switch box, SBX. What we are interested in is in knowing how signals flowing into the interconnecting lines can go from one building block to another one. We know that they can use direct connections, but in our specific case, what we are interested in investigating is in how segmented interconnection can be interconnected by properly configuring the programmable switch boxes. At the end, as the name is suggesting, a programmable switch box is a box of programmable switches. In this figure, we are appreciating the boundaries for the switch box represented by the dotted line, while the switch matrices, the interconnection points, have been represented by the green square at the cross of the two lines. As we have done for the switch boxes, let us now see how a switch matrix is realized. A programmable switch matrix is realized by grouping together a set of 6 programmable switches. Each programmable switch is implemented by using a pass transistor. In the figure, we can see how the 6 pass transistors are connected to implement the switch matrix. Configuring a programmable switch matrix means that we do have to provide the configuration of the 6 programmable switches. Within this context, by numbering each programmable switches, we can define a sequence of 6 bits as the configuration of the programmable switch matrix. In our example, we started to count from the pass transistor on the top left corner. Therefore, a 100000 configuration is used to enable the pass transistor on the top left corner while leaving the other open. This will, as an example, enable a signal to go from the top to the left of the switch matrix. A 010000 sequence, on the other hand, will enable the top right pass transistor, allowing a signal, as an example, to go from the top to the right switch matrix. Following this schema, a 001000 is the configuration to enable the bottom right pass transistor. To complete the set of the external pass transistors, we can now easily imagine that the 000100 sequence will set the bottom left pass transistor to enable a signal to go, as an example, from the left to the bottom of the switch matrix. A 0-0-0-0-1-0 configuration will enable a left-to-right communication, while finally a 0-0-0-0-0-1 sequence of bits will enable a vertical path for the signal going into this switch matrix.